This video is about random variables and their distributions. We say we know the distribution of a given random variable if we know all probability values associated with the random events generated by this random variable. So essentially, distribution need to specify a distribution of a random variable need to specify all probability values of all the events generated by a random variable. This video discusses distributions concerning particularly real-valued random variables and discrete random variables. We know real-valued random variable, for example, if we pick one, x would map elements from sample space S to real numbers. And we can use x in C to denote random events. A random event containing all the outcomes such that x would map those outcomes to values within C. And here C is some subset of the real line. Then the distribution of a given real-valued random variable need to be able to specify all probability values of the events generated by the random variable x. So essentially, the distribution need to be able to specify all probability values associated with such events generated by random variable x. For example, it needs to be able to answer what are those values. What are the probability values of event, for example, x equal to e? What are the possible values of an event x in such union of intervals? There are so many associated events. Luckily, we only need to know probability values of some selected events, and the rest probability values can be easily inferred from these values. For example, for real-valued random variable, we only need to know the CDF function to know the distribution of this real-valued random variable. The CDF function is the cumulative distribution function. It's the function usually denoted by fx, where we use the capital X here in the fx to denote the random variable x that maps numbers to numbers within 0 and 1. And its definition is by this formula, which is fx small x equal to the probability value of the event random variable x smaller or equal to this small x. So essentially, it means in order to know the distribution of a real-valued random variable, we only need to know probability values of the following types of events. Random variable x smaller or equal to a small x from the real line. That is to say, we only need to know the CDF function to know the distribution of a real-valued random variable. This CDF function has some special properties. You can pause the video here first and think what kind of properties this fx function has. Okay, the first property is it is an increasing function from 0 to 1. So it takes values from 0 to 1, which is very natural because, right, by this definition, we know it's equal to the probability value of some random events, and we know those values are always within 0 and 1. At the same time, it is also increasing from 0 to 1. This is also quite easy to think about, because if we indeed have x1 smaller or equal to x2, then we would know this event, capital random variable x, capital X is smaller or equal to small x1, will always within the set within the event of x smaller or equal to this small x2. And according to axioms of probability, we know this probability value of this event will always be smaller or equal to probability of this event. And therefore, the fx small x1 is always smaller or equal to fx smaller x2. Particularly, we could take a look at those two limits. The first one is the limit of fxx. If we let this small x within the bracket goes to negative infinity, this limit goes to 0. Or if we let small x goes to positive infinity, it goes to 1. The reasons behind it is also quite intuitive, because for real values, random variable, we know x maps everything to real line. So it only takes numbers from the real line. If we let this x goes to negative infinity, then there is nothing from the real line. This is essentially the probability value of an empty event. Then according to the axiom of probability, we know it's 0. For the second one, reasoning goes in a similar way. Because if we let x goes to positive infinity, then essentially this is gonna cover the whole real line. And x only takes values from the real line. It contains all the values from the real line. So it's essentially equal to the probability value of the sample space. According to the axiom of probability, we know it's equal to 1. So this is the first property associated with this CDF function. The second one is a little bit abstract. It's called right continuous, which is the fxa is equal to the limit of fx if this x decreases to a. And all CDF functions, they are right continuous. They are always right continuous. However, this equality may not be true, does not hold all the time. fxa may not equal to fx if we let small x increases to a. Right? This may not be true. But this is always true. And later on, we're gonna, near the end of this video, we're gonna show one simple example to illustrate this abstract property. Those two properties are quite important actually. If we have any functions maps numbers to numbers within 0 to 1 satisfying those two properties, those functions are potentially CDF functions. Okay, now let's take a look at one simple example. We say that to know the distribution of a real valued random variable, we only need to know the probability values for certain type of random events generated by those random variable, right? In the real valued random variable case, we only need to know the CDF function. So let's consider this simple example. Let x denote the random variable that equals the number of heads if we throw a coin 10 times. So if we know the distribution, if we know fx, it should be easy to calculate like probability values of this event, x equal to 6. Right? Because we already discussed this statement that if we know CDF, we should know the whole distribution. If we know the distribution, we should be able to specify all probability values of random events associated with these random variables. So we should be able to calculate this value using values from the CDF function. And indeed, it can be calculated in this way. We can pause the video at this moment and think about why. The reason is quite simple, right? According to the definition, we know fx6 is equal to the probability of x smaller or equal to 6, which is essentially the probability value of this random event, which is x either equal to 1 or 2 or 0 or 2 until 6, right? Similarly, the fx5 equal to the probability of this event, x either equal to 0 or 1 or 2 until 5. So the difference of those two values based on axioms of probability value we know should be equal to the probability value of this event, which is x takes value 6, which is probability value x equal to 6. So indeed, if we know CDF, all the other random events, the probability values associated with other random events should be easily inferred from the CDF function. Well, for this special case, there should be easier way to specify the distribution of this random variable, of this real values random variable, because it at most takes 11 different values, right? We only need to know probability value associated with such random events to know the whole distribution of this random variable x. So for discrete random variable, indeed, we have something simpler to look at, which is probability mass function. For real values random variable, CDF would specify the whole distribution of this real valued random variable. But if it's also a discrete random variable, then we only need to know the probability mass function to know the whole distribution. The probability mass function is essentially pxx. Usually we use this px to p capital X to denote the probability mass function of a discrete random variable x. And it specifies all possible values, all probability values of event x equal to x, with small x come from the support of this random variable x. So it basically says, if we have discrete random variable, we only need to know probability values of the following types of events: x equal to small x, x with small x from the support of x, in order to know the distribution of this discrete random variable. And again, PMF function also have some special properties. Non-negativity. So it always takes non-negative value, actually positive value if x from the support of random variable x, and 0 otherwise. And the second property is, you can think about yourself. You can pause the video here and think what kind of properties need to be satisfied by this PMF function. Well, the second one is the summation gonna be equal to 1. Right? Suppose if we have support of x equal to x1 to x2 and keep going, then if we sum up all the PMF functions evaluated under those values, the summation will be equal to 1, which is also intuitive if you understand well the axioms of the probability, right? So this one is essentially equal to the probability, again, the whole sample space. So it has to be equal to 1. Again, if we have a function satisfying those two properties, these functions are potentially PMF functions of some discrete random variables. Okay, those are the distribution function associated with real value random variable and discrete random variables. They basically tell us almost everything we need to know about a random variable. Let's take a look. Another simple example, right? Throw a fair 6-sided die. So after the introduction of so many abstract concepts or definitions, let's take a look one simple example from our daily life to concretize all those abstractions. So suppose we throw a fair 6-sided die for one time. Then what is the PMF function for the random variable x? X denotes the number of eyes of the outcomes. If we throw this six-sided fire die for one time, you can pause the video here and think about it yourself. Well, the answer is quite simple, right? So X only takes six possible different values. Either has a 1 as a result, or 2 or 3 until 6. And because it's a fire die, so each outcome takes, they are equally likely, and the probability of this certain event, X equal to I, is 1/6. Now, we know PMF. If we know the PMF of a discrete random variable, we should be able to specify the whole distribution of this random variable, right? And we should also be able to derive the CDF function, the cumulative distribution function of this discrete random variable. So you can pause the video here and see if you can draw the figure of this CDF function. Okay, here is the results. From the PMF, indeed, it's easy to derive the CDF as well. This is the graph of the CDF function associated with X. So this is the draw of fx, and the horizontal line is the value taken by small x, and here is fx. Apparently, we can see it's an increasing function, right, from 0 until 1. So here is equal to is the point that small x equal to 1, and we observe a jump in values of this function from 0, and it jumped to 1/6. And this is 2, another jump by the value of 1/6. And right after 6, it's gonna always take values of 1. So it's indeed a 0, 1 function, an increasing function from 0 to 1. And furthermore, if we look at those values, right? For example, if I look at values at this point, so suppose now we look at values at this point, indeed, fx2 is equal to the limit of small x decreases to 2 fx small x, right? However, if we move from the left hand side, well, this one will end up here, which is not the value of fx2. So at this point, the function is indeed right continuous, but not left continuous. Well, if we take a look points here, it's both left and also right continuous. But for this CDF functions, for this CDF function, it's always right continuous, but not always left continuous, right? So this illustrates the second property associated with the CDF function. Now, if we throw a fair six-sided die twice, what is the PMF function of y, the sum of two die rows? You can pause the video here and think about it yourself. Well, essentially, if we want to specify the PMF of y, you have to calculate the probability of such event, right? With I equal to from 2 to 12, because it's at least to be equal to 1 plus 1, right? And the maximum number could be 6 plus 6. You can try to calculate the values, probability values of these random events, and try to think about how those numbers are linked with numbers presented here. Okay, thank you for watching this video.